When we build machines to explore the cosmos, we're not just fighting against, huge distances and the vacuum of space. We're fighting against temperature. The unbelievable, unimaginable cold of deep space is one of the absolute biggest challenges for our electronics. So let's dive into this quest for a tiny component that can actually survive the freeze.
It's a good question, right? I mean, we stick our food in the freezer to make it last longer, but for most electronics, extreme cold is basically a death sentence. The physical properties of all the materials inside them just change dramatically. And components that are supposed to be rock solid and stable start to drift, making the whole system totally unreliable.
And we're talking really cold here. Way out there, far away from the warmth of any star, temperatures can drop from about room temperature, that's around 300 Kelvin, all the way down to just a few Kelvin above absolute zero. Your standard off-the-shelf electronics? They're designed to work in a much, much cozier range. So how do you build a machine that can be reliable in space? Well, you have to go right back to the basics, one tiny component at a time.
And that brings us to the hero of our story today, the Zener diode. It might look small and pretty simple, but its job is absolutely critical. You can think of it as a gatekeeper for voltage. See, a Zener diode is often used as what's called a shunt voltage regulator. The best way to think about it is like a dam for electricity. If you've got this unstable, fluctuating river of power coming into your circuit, this little guy diverts any excess, making sure that what comes out the other side is a perfectly steady, constant, and predictable flow. And that stability is everything for sensitive circuits. So here's how that dam actually works. The graph on the right is the real key. Just look at how, as the current changes, the voltage hits one specific point. We call that the Zener voltage, and then it stays almost perfectly flat. That flat line, that's our stable, predictable flow of power. That right there is the magic of this little component.
But of course, here's the problem. As you get colder and colder, the physics inside that diode, well, it starts to get complicated. A battle begins between two completely different physical phenomena, two different kinds of electrical breakdown.
And this slide lays out the two forces at war perfectly. On one side, you got the Zener effect. It relies on a quantum thing called tunneling. It's dominant in low voltage diodes, and it has a negative temperature coefficient. That means as it gets colder, the breakdown voltage actually drops. On the other side, you have the avalanche effect. This happens in higher voltage diodes, and it's kind of like a tiny microscopic snowball effect. It has a positive temperature coefficient, so as it gets colder, the breakdown voltage rises. So you've got one force pulling the voltage down and another one pushing it up. So scientists had a really clear question. In the extreme cold of space, which one of these effects is going to win? And to find out, they designed an experiment to throw these little components into what you could call a cryogenic gauntlet. The setup was pretty straightforward, but absolutely crucial. They took a whole range of diodes with voltages that span this entire battleground, and then they just slowly cooled them down to those frigid deep space temperatures. And the whole time, they were measuring that all-important output voltage, just watching to see what would happen. And the first results started coming in. For the low-voltage diodes, the story was totally clear. As you can see right here in this graph, as the temperature went down, the regulated voltage went down with it. A clear-cut victory for the Zener or tunnel effect with its negative temperature coefficient. But, and this is a big but, for the high-voltage diodes, the exact opposite happened. The colder it got, the higher the voltage climbed. The avalanche effect was clearly in the driver's seat here, pushing that voltage up. So now we've got two opposing, unstable behaviors, and neither of them is what you want for a mission to, say, Jupiter. Okay, so this is where the whole investigation gets really, really elegant. I mean, think about it. If one effect pulls the voltage down and the other one pushes it up, what if you could find a diode where they just perfectly balance each other out? A Goldilocks diode that's just right. The whole entire experiment really comes down to this one question. Can we find a component where this internal tug of war results not in chaos, but in perfect, beautiful stability? And this graph, this is the money shot. This single chart holds the entire answer. Okay, let me walk you through it. On the horizontal axis, the one on the bottom, we have the rated voltage of the diode being tested. On the vertical axis, we have how much that voltage changes with temperature. And a value of 0 on that vertical axis, that means it's perfectly stable. So let's decode what we're seeing here. Look at the diodes below about 5 volts. Their stability factor is negative. That means the Zener effect is winning, pulling the voltage down in the cold.
Now look above 6 volts. The factor is positive. The avalanche effect is winning, pushing the voltage up. But do you see it? Do you see where the line crosses zero? Right there, in that sweet spot between about 5 and 6 volts.
It turns out, in that super narrow range, the two effects don't just compete, they completely cancel each other out. That negative pull from the Zener effect is perfectly matched by the positive push from the avalanche effect. And the result? A component that is almost perfectly immune to the cold. Its output voltage just doesn't care if it's at a comfortable room temperature or deep in cryogenic territory.
Now, this is so much more than just a cool piece of physics. It has profound, real-world implications for how we explore the universe. The takeaway here is incredibly practical. Engineers now have a simple, clear roadmap. If you're building a satellite or a deep space probe and you need a stable voltage reference, you don't need some exotic, custom-built, super expensive technology. You just need to select an off-the-shelf Zener diode with a breakdown voltage right in that 5 to 6 volt Goldilocks zone.
It's just a beautiful example of how understanding fundamental physics can solve a massive engineering challenge. And it really leaves you with a final thought. With reliable electronics that can withstand the absolute harshest environments in our solar system, what new frontiers can we now explore? What mysteries are we now equipped to solve?